Today I have two consumer grade uninterruptible power supplies. These are the battery backups that you typically buy for your computer, your home entertainment center. These are used. These are ones that I purchased with my own money. Both of these models advertise a stepped approximation to a sine wave waveform. So now what do I mean by that? So a true sine wave power that comes out of your outlet should look like just that, a sine wave. I got my oscilloscope here, so I'll illustrate what that should look like. Don't do this at home unless you really know what you're doing and get yourself killed. So see here, that's what sine wave power looks like out of your outlet. Notice that the waveform is nice and smooth. The power is always, or the voltage is always changing. There's no flat spots. That's what you want to see. And as you can see, that's almost exactly 60 hertz. And this is attenuated, so this signal is reduced a bit, but it should be about 120 volts RMS. Okay, so take a mental picture of that. Now what we're going to do is we're going to see what that same waveform looks like on each of these UPSs. Okay, so first we're going to go with the APC Backups XS1500. Battery is a little old, but it's fully charged. Unit is functional. So I'm going to plug power cable into the back of this. Pray I don't short anything out in doing so. Okay, so we should see the same waveform that we saw out of the wall, because right now it's not on battery backup. Okay, so roughly the same thing. I'm going to pull the power from this APC and we're going to take a look at how it changes. So let's yank this power cable out of the wall. You hear this thing, the fan going now. It kicked on into battery backup mode. Now, what the heck is this? That doesn't look like the same waveform, does it? So, what's going on here? This is the bottom of your quote-unquote sine wave coming up, going to 0, and that'll be key, so remember that later. You come up positive, come back to 0, then negative again. And you can see the scope is even having trouble zeroing in on us. A lot of these measurements are freaking out a little bit. You can see on the display. Again, this is also attenuated, so you're not going to see 120 volts RMS. This is attenuated 10x. But they call this a stepped approximation to a sine wave. I could build a circuit in about 10 minutes that builds this type of stepped approximation to sine wave. This is not a very impressive. So a lot of what they call active power factor correction power supplies, basically any power supply on a computer that is 80 plus certified or better, may have a problem with this waveform because of this 0 point here where the voltage is 0, the power is 0. So those power supplies, because of their efficiency, and I won't go into the physics behind it all, they may view this as essentially no power, and they may not work. Okay? So in my personal opinion, I'm not an electrical engineer, but I know a thing or two, or at least I like to think I do. That's not a very good waveform for a device that's designed for pure AC power. That's not a very good waveform for a device that's designed for pure AC power. Now, let's unplug here. Let's go to the cyber power unit. Let's plug this thing back in. Shut the fan off. Okay. Let's go to this cyber power. This is an 825 AVR. Again, these are all used. All purchased with my own money. No one's paying me to do this. Let's see what we see here. Let's turn it on, I guess, too, right? Okay, so this is plugged into the wall. Well, that's a really goofy waveform. What? There we go. That's better. So this should be wall power. So Getting pretty close to what we saw before. Nice smooth wave, about 60 hertz. Now let's unplug it. Make it go into battery backup mode. What the heck? I'm not sure what this is, but this is horrible. Let's do a roll so we can see. Let's dial this back a little bit. This is an absolutely horrible waveform. I mean, this is almost difficult to read. It's so bad. I'm not sure what this is supposed to be. So it looks like in this very rudimentary test, the APC did a much better job. I mean, at least you could kind of see the resemblance to a sine waveform. This one, I'm struggling. I'm not the smartest guy in the world, but nor am I an electrical engineer skilled with using these things, but yeah, so not a very pretty waveform. And its battery's probably about to die. Alright, so you guys see what these relatively inexpensive consumer grade, and I want to emphasize these are consumer grade. This is not the type of equipment you would use in a server rack. But this is what you might buy on Amazon or at Staples or Office Depot or wherever these things are sold. These are, again, stepped approximation to a sine wave. They didn't look very approximated to me, but that's my personal opinion. I have ordered a true sine wave unit by this same company, CyberPower. It was about $200 for a capacity similar to this, 1500 volt amps. So we'll see how that performs on the oscilloscope. True sine wave, we would expect a waveform similar to this, not too different from this. So that should be here in a couple of days, and we'll pick it up then. Okay, so I lied a little bit. So before we wait for the new one to arrive, I just want to do a brief demonstration of why that waveform matters. So I've plugged in an electrical fan. It's not in battery backup mode right now. Remember, this is the UPS that actually seemed to perform a little bit better. And turn on the fan. So this should be as if the fan was running off the wall outlet, because it is. So notice, this is the max speed now. I don't hope you guys can hear that, but it seems to be chugging along pretty good. I'm going to unplug it, and notice how things change. I don't know if you can hear, but the fan's starting to hum pretty loudly. It's slowed down a bit. I'm going to plug it back in again. Notice that humming died almost instantly and the fan picked up. So, AC induction motors, of which this is one, they like true sine wave power. And again, a lot of the newer computer power supplies and possibly other types of power supplies that use active power factor correction are designed for sine wave power. So you really can't use these types of things anymore, these stepped approximation to a sine wave power supply, at least the ones that do such a poor job at it, in my personal opinion. So again, we're going to pause a couple days. Should have a new one of these that is true sine wave power coming in. So our friends at Amazon have dropped off a new battery backup. This one is advertises sine wave output, not approximation of sine wave, sine wave. So let's unbox this and stick it on the scope. Okay, got everything unboxed and packaged. And even here it says that it supports active PFC power supplies. The CyberPower UPS system supports high-efficiency power supplies with active power factor correction. Active PFC is used to improve the efficiency of delivery. So this power supply should be pretty close to what the wall looks like. Got the UPS turned on by simply holding down the power button for 2 seconds. We'll cycle through the display, see what we see. Nothing too earth-shattering yet. It says the battery is 100%. 0 events. 123 volts input, 123 output, 60 hertz. Now this should be a line interactive power supply, and those types of power supplies do not condition the power that comes from the utility. So as long as the utility power is present and it meets the standards that this thing deems, it will just pass through that utility power. So if you have noisy utility power, this won't do anything to help you. They do make UPSs that will do that, but they're far more expensive, way out of this price range. Alright, so let's plug it in and give it a test. Okay, so there's our waveform on utility power. About what we would expect to see. This signal has been attenuated 10x, so don't pay too much attention to the numerics, but the waveform itself is what you want to focus on. And we're getting almost exactly 60 hertz again, which is what we'd expect in the United States anyway. Let's unplug the UPS and see what happens. Wow. Anybody see a difference? That's pretty darn good. Holding rock solid at 60 hertz. I didn't see really anything in the waveform change. Did you? Let's re-trigger and see if we see any subtle differences. Let me get this thing zoomed in on one of the peaks so we can see what it actually looks like. Okay, so that's the peak on utility power. Pretty smooth. Let's take a look at that when we were on battery power. To be honest with you, it actually looks a little bit better on battery power. It's pretty darn impressive. So again, that's battery, utility. Notice the utility is a little bit flatter at the peak, whereas on battery it's a little bit more round. So overall, I would say this UPS is a real solid winner and real solid performer. Again, having only unboxed it now and not putting it to a long-term test, the waveforms are infinitely better than the stepped approximation to sine wave units like that older cyber power unit that I had laying around that didn't really do its job, and the APC. So APC probably does make one of these true sine wave UPSs as well, but I don't have one of those, so unfortunately I can't compare these two side by side. But certainly this unit, based solely on this testing and what the scope looks like, seems like a real solid performer.
So, ladies and gentlemen, we've got a UPS power supply, some battery, backup, surge protector, etc., etc. And it's got a real cheap inverter, I believe. I'm absolutely sure it's got a cheap inverter because let's go ahead and we're going to unplug it. Now this is APC backup UPS ES750 surge protection, and what we have here is my standard electric meter, and we're going to test between ground and power. If it's a good inverter, there should be 115 volts between ground and power, which here's your ground and here's your power. I'm going to switch on to VAC. We should have 120 volts ish here, and it's 56 on one circuit and 58 on the other circuit. So that means between the two you've got 115.1. So what I took the liberty of doing is cutting one of my appliances. I'll have to wire it back up later. It was my table saw. I just borrowed the cord that I already put on there once. I cut all the wires to where they're not directly attached. And now we have live wires. This is a UPS, and here's the ground circuit. It's not attached to ground right now, so it can't follow back through to our key sight scope through its ground. So I'm going to grab a hold of this. We're going to check one side of the wave and the other side of the wave. I'm going to hold these so it doesn't fall, etc. I'll switch this to 100 to 1. I'll do auto scale. And look at that. It's a modified square-ish wave. And it's awful looking. It is so bad looking. The wave itself is just terrible. But I don't think that's the worst one we have here. I actually think this is this is a better one than, this one that's in the server rack. The one that's in the server rack buzzes and it makes everything else buzz. So we're going to test that one as well. But we also have another UPS, two of them. They're identical. We'll test one of them for the sine wave. The batteries went bad on these and I got them for free. So thanks for the person that got them for me for free. Too bad he don't watch the videos. So we've got this right here, and you can see the sine wave is garbage. I'm going to plug it back in to our standard circuit. And that, my friends, is the sine wave from the Sine inverter. So that's a different UPS power supply. I'm going to have my wife give me a hand and go flip the solar power off, and we're going to check the grid power sine wave. Now, that right there is a super clean sine wave. You can see how it goes up and then it falls back down and goes up and falls back down. The Sine is similar to that, I suppose, but not exactly the same as the grid power. The grid power is a bit better than the Sine, but this one for sure is the worst out of the three. Let's test another one. So for this test, we have this power inverter. I'm going to press the power button and turn it on. Alright, so the green light, and it shows the sine wave, there's a green light. And I hear it buzzing. I'm assuming it's charging the batteries because the battery light is flashing yellow. And we're going to check our voltages with the electric meter first. And remember how we had the same voltage between ground and power. It should, if it's a good inverter, we shouldn't have anything between ground and neutral, but we should have, so if it's a good inverter, we should have pretty much 0 volts between ground and neutral. And that's what it appears to be, 0 volts between ground and neutral. (124) between neutral and power. 123 between neutral and power. So that's the grid power, that's normal. But when we unplug the wire going to the supply, I bet you it'll go back to being a crappy inverter like the other one. It's unplugged. I can hear buzzing. Let's check neutral to ground. Nothing. That's an excellent sign that the inverter isn't shorted between neutral and ground. So we'll check here. $122 volts. Excellent. Now we can go ahead and check the sine wave easily. There's one side and the other side. Ladies and gentlemen, this is a pure sine wave inverter. Right here, this is a really nice power supply. It is a model ONE254, but it's not something that you're going to find a lot. For instance, this power supply directly is a very expensive one. Let's see if all the terminals look exactly the same. So yeah, it looks good. So basically I found these, they got bad batteries. You'll find these probably on eBay pretty cheap. I bet you'll be able to find them pretty cheap. If you want to put your electronics on this thing is going to be super efficient. 12 volt battery setup. It's a pure sine wave. It's safe to plug your electronics into. It's not going to hurt it. It's not buzzing. It's not making any funny sounds. And you can see the sine wave. It's nearly a pure sine wave. It's not perfect, but it's almost pure. So if we zoom in and widen it, you can see we got a dip here. I mean, there's obvious that it's not a perfect sine wave, but I would consider this a pure sine wave over the last one, the modified sine wave, which is pretty much crap, garbage, useless. This thing is going to be super efficient, and it's going to charge your batteries really well. You know, charge your laptops, charge your cell phones, charge, like I had a modified sine wave inverter kill my it killed what I had before. We'll move on to the next one. Okay, ladies and gentlemen, we now have this Cyber Power rack inverter. Now, you know, you think a rack anything is great. Well, I have to disagree, because you know, this inverter buzzes whenever you put a load on it. It sounds like it's gonna die. It doesn't last a long time, but I was told it has lithium batteries inside. Now, if it's not that good of an inverter, I mean, there's no reason to really keep this thing as my rack inverter, because that thing is like thousands of watts, you know, 1,000 watts to run everything on the rack. And I don't think this is that good of an inverter, but let's check it out. So I'm going to turn the power on, and we're going to check from ground to neutral. So we're checking from ground circuit to neutral. Okay. Now I have 0.4 volts, and that's with it not inverting. It's at 100% capacity. It's got 100 minutes, 0% consumed. So what we're going to do is we're going to disconnect the inverter and test between ground and power. That's a different one. Sorry. So we're going to disconnect it. Now this one is running off of its battery pack. It's beeping. So we got ground, 51 volts. That's a bad sign that it's a crappy inverter. Let's go ahead and check the voltage right off of it. 114 volts. This one says 120 volts, so it's like 10% off or whatever. So obviously this voltage meter is terrible, and not to mention whatever else is inside of here. So let's look at it on the sine wave. I'm gonna turn it off. We'll move our inverter out, our thing out of the way, and then we're gonna check this circuit and that circuit. So you got that one, and the neutral's disconnected. We're going to go ahead and power it up. Okay, so right now you see our sine wave. So I guess it's testing. Or something. So we're going to zoom into our sine wave a little bit. So that's our zoom that we're going to hold at. This is 120 volts offset from center to top and bottom. So right now we're going to go ahead and disconnect the power to the rack UPS. And that has got to be the worst sine wave that I've found in the house yet. Let's take a closer look. Let's widen it. And you see it's got sharp pickups, and then just, you know, signal drop-offs. This is a square wave that is terrible. It's the worst square wave you can have. It just goes down, up, up. The worst square wave you can have. Just goes down, up, up, down, down again. So up, up, down, down. I mean, that is a square wave. That's not even a modified sine wave. It's a square wave, and it is the worst, you know, that you could get. It said it's 400 watts, you know, output. So this thing is supposed to be able to do 400 watts, but it has a 700 VA, which doesn't seem to make sense. It should be able to handle a lot more than that. Now I'm assuming that it works better with the load on it, but even with any electronics that you're going to run into, putting a square wave on it kills it. Don't do it. You're a moron if you do it. And this is why you get voltage peaks, and then they hold that voltage for that period of time, and then it stops and drops off, and it just kills it. So this is a square wave sine, and it's terrible. Don't get a square wave inverter. Don't get a modified sine inverter. Get a pure sine inverter like this one or a Magnum. Like I said, you can get one of these really cheap to put your expensive stuff on. This isn't going to hurt like a refrigerator if you could run it, but it's too small to run a fridge. You're going to need like 2,000 watt surge to do that, and these have zero surge. So that's it for today's video. I'm showing you the UPS power supplies that I've got, and I hope you guys